a 3D printed component fails. Was it the design, the printer, or something more fundamental within the material itself? Often, the root cause lies deep within the unique material science of additive manufacturing, a realm where polymers and metals behave under profoundly different rules, leading to distinct failure modes frequently misunderstood. This difference, often overlooked, dictates everything from part strength to structural integrity, revealing why seemingly robust prints can unexpectedly fracture. The very nature of layer-by-layer fabrication introduces inherent anisotropies. Unlike traditionally manufactured parts, 3D printed objects are composite structures at a micro level, built from discrete layers that dictate stress distribution and potential weaknesses. This layered construction fundamentally alters how materials respond to external loads, creating a critical challenge in predicting long-term performance and reliability. Polymers, with their long, chain-like molecular structures, exhibit complex behaviors under thermal and mechanical stress. Their properties depend heavily on factors like molecular weight, chain entanglement, and the degree of crystallinity. In 3D printing, the thermal history of each layer profoundly impacts these characteristics, influencing everything from elasticity to ultimate tensile strength in ways conventional manufacturing does not. A primary failure mechanism in 3D printed polymers is interlayer weakness. During deposition, new polymer layers fuse with previously deposited ones. However, insufficient thermal energy or cooling rates can hinder proper chain diffusion and entanglement across these interfaces. This results in weak bonds between layers, creating planes of reduced strength susceptible to delamination or fracture under loads perpendicular to the print direction. Thermal management during polymer printing presents another critical challenge. The controlled heating and cooling of successive layers generate internal stresses. Differential cooling rates across a part can lead to warpage and residual stress accumulation. If these stresses exceed the material's yield strength, micro cracks can form during printing, compromising the part's integrity even before it leaves the print bed. Furthermore, certain polymer failures stem from environmental factors. Many photopolymer resins used in SLA and DLP processes continue to cure and degrade under UV light exposure, leading to brittleness over time. Similarly, hygroscopic polymers like nylon absorb moisture from the atmosphere, which can plasticize the material, reducing its stiffness and strength, or lead to bubbling during subsequent thermal processing. Metals, in stark contrast, possess a crystalline atomic structure characterized by strong metallic bonds and a regular lattice arrangement. Their properties are governed by grain size, crystal orientation, and the presence of dislocations. In metal additive manufacturing, the rapid solidification involved in processes like selective laser melting or electron beam melting creates unique microstructures that fundamentally differ from their wrought or cast counterparts. One critical failure mode in 3D printed metals arises from their distinctive microstructure. The extremely rapid cooling rates induce fine, often columnar grain structures, which can lead to anisotropic mechanical properties. These elongated grains, oriented along the build direction, can create preferential paths for crack propagation, making the material weaker in certain directions and more susceptible to fatigue fracture. Porosity constitutes another significant weakness in additively manufactured metals. Incomplete fusion, gas entrapment, or keyhole formation during the melt pool dynamics can lead to internal voids. These pores act as stress concentrators, reducing the effective load-bearing area and providing initiation sites for fatigue cracks, thereby drastically diminishing the material's overall strength and ductility. Residual stresses are particularly pronounced in 3D printed metals due to the extreme thermal gradients experienced during processing. The localized melting and rapid solidification, combined with the constrained nature of the build, induce significant tensile and compressive stresses within the part. These stresses can lead to part distortion, cracking during printing or post-processing, and premature failure in service. The divergence in mechanical properties between 3D printed polymers and metals is substantial. Polymers typically exhibit lower stiffness and strength but higher elongation, deforming plastically through chain uncoiling and slippage. Metals, with their rigid lattice, deform through dislocation motion and slip planes, leading to higher yield strengths and hardness, but often less ductility before fracture, especially with introduced defects. Thermal properties further differentiate their behaviors. Metals boast high thermal conductivity, efficiently dissipating heat. Polymers, conversely, are thermal insulators, retaining heat, which directly influences layer fusion, residual stress, and warpage. This fundamental difference necessitates entirely distinct thermal management strategies and process parameters for each material class. Addressing these challenges often involves sophisticated post-processing or the development of hybrid materials. For polymers, annealing can improve interlayer diffusion and reduce residual stress. For metals, hot isostatic pressing densifies parts, reducing porosity, while heat treatments refine grain structures. Furthermore, fiber-reinforced polymers or metal matrix composites attempt to leverage the strengths of both material types. Predictive modeling plays a crucial role in mitigating failure. Computational tools simulate thermal histories, stress distributions, and microstructural evolution, allowing engineers to optimize print parameters and part geometries. Understanding the interplay between process, material properties, and expected loads is paramount to designing reliable 3D printed components and preventing catastrophic failures. The science of why 3D print materials fail is a complex interplay of polymer chain dynamics, metallic lattice imperfections, and the unique thermal cycles of additive manufacturing. Mastering these materials science principles is not merely an academic exercise, but a critical imperative for unlocking the full potential of 3D printing, moving beyond rapid prototyping to reliable end-use production across diverse industries.